Hello everyone, welcome to the Kinematics and Dynamics of Machinery class. In this course, we're gonna start a new topic, which is the dynamic force analysis of mechanisms. And in this video, I'm gonna give a little bit introduction about this topic, which again is the dynamic analysis of or force analysis of mechanisms. This is gonna be like in order to do force analysis, we have to finish first the kinematic. Right? This is the kinetics, as we discussed in the start of this course, that we are interested in the mechanics of these different mechanisms. And the mechanics, it is a general branch of science or a field of science that include two main branches. Like the first one is the kinematics, and this is what we already discussed so far through this course, starting from the beginning till the cam mechanism. Even the cam mechanism, we didn't account for the force or the weight or the mass of the different components or the force that would be generated between the different elements of a mechanism. We didn't account for that. So it means that we were just interested in the kinematics of this mechanism, investigating the displacement, the velocity, and the position and the acceleration of the different elements and the different components and points that belong to a certain mechanism. And we use different approaches, two main approaches: analytical method using the complex algebraic method and the graphical method for these different mechanisms. Now we're gonna move to the force analysis, to the second part, which is the kinetics. The kinetics, it means that we're already interested in investigating how this mechanism is going to move under the influence of different forces. Or in other words, we're gonna try to answer this question: how about if this mechanism is subjected to a force with a certain amount, what should be the velocity, acceleration, and the position of this mechanism? We can answer these things, but to do so, we have to consider the dynamic force analysis of this mechanism or this object. It is very similar to the dynamic course that we already discussed before, or it is very similar to the static and the dynamic class that you had before, especially the dynamic course. So this is the main objective of this topic. Again, we're gonna focus on the dynamic force analysis. So what does it mean, a dynamic force analysis? Or you could say that this is like the inertia force. This is the type of force that is related to the acceleration by which an object is moving. And I'm pretty sure that you have an idea about this inertia forces before, even starting from the physics class. You should understand that this inertia, it is kind of resistance of the object, that the object produce a response if we try to change its state. If the object is already stationary, standing, not moving, there is kind of resistance to change its state. Or even if we don't have the object that already moving with a certain velocity or a certain acceleration, and you for some reason try to change its state, you have to subject this force, this object, into some forces according to Newton's law, and this force should be equivalent to its inertia force. So you could consider that this inertia force is kind of resistance that the object generates, or this is like the way by which the object tries to resist your tendency to change the state of an object. The state, it would be the current state of the object, whatever it is moving. It is moving with a constant velocity or different velocity, or it is stationary. So if you would try to change the state of this object, we have to subject the object into some force. We have to apply some forces according to Newton's law, as I mentioned, and this force should be equivalent to the inertia force. So the inertia force, or the dynamic force, it is the force that generates due to the object's motion with non-uniform velocity. The key condition here, that the object should be moving with non-uniform velocity. Non-uniform velocity, it means that we're gonna have an acceleration, because the definition of the acceleration from physics, it is the rate of a change of the velocity of an object. So this force depends definitely on the acceleration of the object. If the object has an acceleration, there should be an inertia force. If there is no acceleration for this motion of the object, there is no inertia force. So simply we can define the inertia force as the mass of the object times its acceleration, as you knew from the physics or even the dynamic class before. Like this is the mass of the object m, and this is the acceleration by which this object is already moving. As you know that any force, it should be a vector quantity. So this should be vector quantity that should have two values One is the magnitude, which just the value of the force, like 10 Newton, 10 pounds, whatever it is, and the direction. You used to have a direction for this force. Make sense? So it is a vector quantity. Now, before we go deeply through the dynamic force analysis, let us introduce here the static force analysis. Static force analysis is going to be much more easy to understand the approach or the graphical method that we're going to use for this part to do analysis. But if we decided to start with the static force analysis first, then I'm going to show you how we can adapt this static force analysis to the dynamic force analysis. I'm just going to give you the transition from the static to the dynamic. So you could consider that this is like introduction, as I mentioned, to know how we can do force analysis in general. And again, the focus is on the dynamic force analysis, but to explain it to you and to understand it, let us start with the simplest case, which is the static force analysis. So what does it mean static? If you remember, even from the statics or the physics class before, or even the dynamics, we have discussed these things in the dynamic class. Static, it means that the static equilibrium, it means that the object is already under static equilibrium, and this will be achieved as long as the object is stationary, not moving, there is no motion, so there is no velocity, there is no acceleration. In the meanwhile, in case that the object is already moving but with a constant velocity. So the common thing between these two scenarios or these two cases of the object, that the acceleration, it should be zero. So if the acceleration equals zero, it means that there is no inertia force, there is no dynamic force, it means there is no dynamic state of the object, and instead we do have the static state of the object or the static equilibrium of the object. This is in case that there is no inertia or there is no acceleration in general. So static force analysis, it means is to come up with any unknown force, to do analysis, force analysis, whatever it is, static or dynamic. You don't have a mechanism, you don't have an object. This object is subjected to some forces. Definitely you're gonna know some of these forces, but some other forces definitely will be unknown. To do force analysis, it means that your objective is just to find the unknowns. It is typically the same thing that we used to do for the position, velocity, and acceleration analyses that we discussed through this course. We said that for the position analysis, you are limited for just two unknowns. These two unknowns will be magnitudes or directions of different vectors, or even the same position vector, the same thing for the velocity and the acceleration. So to find this unknown, this means that you have finished, or you already doing force, and you are already doing analysis. So here we would like to repeat the same issue, but for the forces, is to come up with the unknown forces. There are some forces definitely that will be given to us. How about the other unknown forces? To find them, this means that you're already doing force analysis. And remember that we're gonna start with the static force analysis. So it's to determine static force analysis is to determine the forces that acting on an object or over a mechanism by considering its static equilibrium condition. And we said that the condition for static equilibrium, that the acceleration of this object should be definitely zero. So we're gonna consider here some important cases to know how, just to establish this method that we're gonna use through this part, which is the graphical solution or the graphical method of force analysis or dynamic force analysis of mechanism. So we're gonna consider different elements or different cases of the element that would be used for forming a mechanism. As we discussed, even through all the different types of mechanism that we cover through this course, you're gonna find that we do have the elements. It would be either members or links or sliders. These are the common things. We may have the slider that moves over ground. We do have a link that do rotation or even general motion, or a link that slides, or we do have a slider that moves over a link. So we consider all of these different scenarios, in addition definitely to the cam mechanism. So forget about the cam mechanism and these cam systems for now, and just focus on the conventional mechanism that consists basically of links and some sliders. So these are the types of mechanism that we're going to consider for the force analysis for this part. So if we're going to pick a link or a member, as I'm calling it here, a member or a link, and the first scenario or the first case here is two force member. Like this member is subjected to two forces, and the key idea that these two forces already located at the ends of this member. There is no force in the middle of the member itself, but instead all the forces already concentrated at so all forces are concentrated at the member's end. No forces are located in the middle of this member. Like this case, like for example, we may have a member like this one, like a link, and this is one end of this link and another end of this link, and there should be some forces, and the forces already acting at these 2 points. There is no forces in the middle. Also, the link, it would be straight or it would be deformed, or it would be with any other shape. Like this is a straight shape, this is an angle shaped member like this one. So also it will be considered or classified as 2-force member as long as there are forces only acting at these 2 ends. There is no forces except at these 2 points. Or it would be having any other shape, as even we discussed these things before in the dynamic class, even if you remember. Like these are the 2 ends and there are some forces acting over these 2 ends. So if we try to connect these 2 points together with a line, so we're going to end up with a line. This line is going to be the line of action of these 2 forces acting over this membrane. So this, for example, we may have one force in this direction and another force in this direction. The same thing, we may have 2 forces here. So we can combine these forces. If we're already working in 2 dimension, if we're already working in 3 dimension, we're going to end up with 3 forces. We can combine them into one resultant force even. So we can combine these 2 forces into one resultant force. In this way, it's going to be acting. You're going to find that this force, if we did the calculation, we're going to end up with a force, and the line of action of this force is going to be conceded to the line that connects the 2 ends of this membrane. The same thing here. We do have 2 forces here. We can combine all of these 2 forces, or these 2 forces, into one resultant force. This resultant force, if we did the calculations and we define the direction of this resultant force, you're going to find it is conceded to the line of action between these 2, to the line that connects the 2 ends of the membrane. So this is one of the specifications of this 2-force member. Any 2-force member, that the resultant of the force on one end, it will be definitely equal in terms of magnitude. These 2 forces, F1 and this F2, both are equal but of 2 opposite directions. So they do have the same magnitude but 2 opposite directions, and their line of action should be conceded to the line that connects the 2 ends of the membrane. This is essentially specification for any 2-force member, whatever it is straight or deformed with any other shape. The same thing here, that this is the line of action between these 2 points. This is the connection point. If you connect these 2 points, this is going to give us the line of action of these 2 forces. You're going to find one force here. This force, it would be tension, like we're already stretching this membrane, or it would be compression like this case. It would be tension or compression like this case. It depends. Like you're going to have at one end one force and the other end the second force, F1 and F2. Something that you should understand about this M and F1 and F2, that the magnitude of F1, it should equal to the magnitude of F2. The magnitude of these 2 forces, they should be equal, but they should be of 2 opposite directions, either stretching or compressing the membrane, and the line of action, it should be considered to the line that connects the 2 ends of the membrane. Make sense? So this is for the 2-force member, and this is one of the simplest cases. So simply, if you know one of the forces at the 2 ends, you can simply come up with the second force. Automatically the second force, it have the same magnitude value, and its direction, it should be opposite to the original force that is already given. It means that, for example, if F1 is given, we can simply come up with F2. So there is no need to do any analysis, to this membrane, because this is the simplest type or simplest form of the membrane. So there is no need to do any graphical things or drawing anything to come up with the unknown force. Again, to do analysis, it means that to find the unknown force. Any force, it should have magnitude and direction. So in general, we should have 4 parameters. 2 for each one: magnitude for this force and direction for this force, magnitude and direction for the second force. So 4 things. If you already knew 2 things, or even you knew 1 thing, you can come up with the other, or especially you should know 2 things, you can come up with the other two things or other two parameters for this mechanism without drawing, without doing any calculations. It is right away, directly, direct step, direct procedure, that this force, they should have the same magnitude but two opposite directions, and their line of action, it should be considered to the line that connects the two ends of the membrane. Make sense? So this is the first type of the membrane, which is very simple and straightforward membrane type. Now let us move to this one, which is three-force membrane. I'm just trying to give it like step by step, like move it smoothly and increasing the level of complexity of the membrane. Now let us move to this membrane with three forces acting on it, like in such a way that two forces will be acting at its end, plus there is another force that is going to act in the middle of the membrane. What I mean in the middle, it should be, it is not necessary to be in the midpoint of the membrane. It would be at any point that belong to the membrane. Even the more general case, we may have this force outside the limit or the boundary of the membrane, as we're gonna see as we move through this part. So let us, like a typical example of this type of membrane, like we do have this membrane in this way, and this membrane is subjected into to three forces. One force at this end, another force at this end. In addition, there is another force that already acting on the membrane in the middle. So we're gonna have here like F2. This is the middle point, or I'm sorry, this is the middle force. This is what I mean by the middle. It means that it is located between the two ends of the membrane. In addition, definitely we're gonna have one force as F3, and there is another force here as F1 acting over this membrane. You're gonna observe something here as I'm presenting these three forces, that this force is, I'm putting the arrow direction of this force. So what does it mean? It means that I'm pretty sure of the direction of this force, and even I could have the magnitude value of this force. Remember that any force, it is vector quantity that require magnitude and direction. So let us assume that the magnitude of this force, it is 40 Newton. So this is the force value, this is the magnitude value, and this is the direction of the force. Since I'm putting an arrow, it means that I'm pretty sure that this is the correct direction of this force. It is directed this way. Make sense? But how about this force? For F3, for example, it is unknown. We have no clue how much is its magnitude. And this one, we don't know how much is its magnitude. Make sense so far? So also, how about if we knew the value or the direction of F1? Let us assume that the direction of F1, it is known, that it is horizontal, but we are not pretty sure whatever it is going to the right or to the left. So that's why I didn't put any arrow, because I'm not sure if it is horizontal going right or horizontal going left. We are not sure if this point. So for this case, F1, it has unknown magnitude, or its magnitude is unknown, but it has a direction. To us, it is the direction. It is kind of known, although we are not pretty sure whatever it is right or left, but we are pretty sure that it is horizontal. So with in this part, we're gonna assume that you're gonna deal with it like it is fully defined direction, but the magnitude is unknown. But this one, it is fully defined in terms of magnitude and direction. And let us assume that this force F3 is fully unknown. We have nothing to know about this force F3. So for this case, I'm just gonna put it in this way. So if I draw a force in this way, this indicates that this force is completely unknown. So for this case, for this membrane, F3 is completely unknown, but F2 is fully defined as magnitude and direction, as we used to do for the complex algebraic method for the position and velocity analysis, right? And the acceleration. The same thing for the F1. F1, we have no clue how much its magnitude, so the magnitude is unknown, but the direction is known. So if I ask you to count how many unknowns do I have for this problem, for this case, we do have three unknowns. One magnitude of force and magnitude and direction for another force. It doesn't matter to us which is unknown or which is given, you are limited for just three unknowns, so you can solve, you can do force analysis. But if the number of unknowns more than three, we cannot do force analysis. Remember, in the position and velocity analysis, we said that we are limited for just two unknowns, right? If the unknowns are two, we can solve. If they are more than two, we cannot solve. Make sense? The same thing for the force analysis, but instead of we are limited for two, we are limited for three unknowns for the force analysis of a three force membrane like this one or any other membrane. In general, for the force analysis, we are limited for three unknowns for each membrane, for each element within the mechanism. Like this element, it is subjected to three forces. Each one of these forces should have two things, have two data. One is magnitude and direction. So in total, we should have 6 parameters, 3 direction, 3 magnitudes for the 3 forces. You should have 3 of them. 3 of them should be given, and 3 are unknowns. We can find them if we did force analysis. But if the number of unknown more than 3, we cannot do any analysis to this membrane. We have to figure out one of the unknowns to minimize the number of unknowns to be 3 instead of being more than 3. Make sense? So now we can do analysis for this mechanism. Analysis, it means that is to find the unknowns. What are the unknowns? One, magnitude of the force, F1, how much it is, how much is the magnitude and the direction of F3. So if the force is fully unknown, we do know nothing about the force, you're just gonna put it in this way. But you're gonna specify the direction as long as you know the direction of the force, and it is not necessary to know whatever it is, right or left. You should know the line of action of the force. It means that the direction is known or is given, and this is a fully defined one in case that the line of action and the direction plus the magnitude is already given. It means that this is a fully defined force. So the question is how we can find this unknown. This is a 3 force membrane. 3 force membrane. Why? Because there is a force in the end, there is another force at this end, and there is another force in the middle. In the general case, we may have this force outside the boundary or the limits. It means that we may have a force here that is already acting, but it is indirect force that acting on the membrane. It is like indirect force. This is like a very special case that I don't believe that we're gonna consider for most of the mechanisms that we're gonna consider for this part. But in all the cases, we're gonna have this force somehow located at a point between these two ends of the membrane. So 3 force membrane, it is subject to 2 forces at its end plus 1 force in the middle. The balance between these forces require a closed force polygon. So the question is how we can find the unknowns. To do force analysis again is to find the unknowns, and to do so we have to draw a force polygon or a force diagram for this membrane. This first polygon, we're going to use it to come up with the unknown force as I'm going to show you. For this membrane, we can draw a force polygon, but 3 given data should be known, and thus we can draw the force polygon to find the other 3 unknowns. Like 3 will be given, 3 will be unknowns, we can apply or we can draw the force polygon for this mechanism. Make sense? So how it works, how we can draw the force polygon for this mechanism. It is very simple. We're gonna start as we used to do even for the graphical method for the position, velocity and acceleration analysis. We have to start with a 0 point, the start point, the origin point of the force polygon. So I'm gonna use another color here for generating this force polygon. So I'm gonna start, let us assume that this is the point OF. This is the original point, this is the 0 point of the force. Then your objective is just to start with the force vector that is already fully defined, which is this one, like this one. This is Fourier, is already fully defined, and we are pretty sure of its direction is already given. So what you're gonna do, your objective is just to pick suitable scale for this 40 Newton. So let us assume that the 40 Newton, this is the scale that this is the scale. So the 40 Newton, I'm gonna draw this one like 4 centimeters. Or like 40 millimeters, it's up to you. So, which is equivalent to 40 millimeter. So your objective from this point, you're just gonna draw a line that is completely parallel to this line. So from this point, you're just gonna draw a line. And make sure that this line is completely parallel. I'm gonna use another color like this one. and I'm gonna draw a line that is completely parallel with any length initially to the F2. This is gonna give us the locus for the endpoint of this force. Starting from this 0 point, your objective is to measure 40 millimeter or 4 centimeter over this line and mark a point. This is going to give us the end of this, the end point. Then your objective is just to connect these 2 points together to end up with the first line for the first force, which is F2. So this is going to give us F2 vector. Make sense? So we do have the start point and the end point of this force vector. Make sense? Then these 2 points, from one point, one of them you're gonna draw F1, from the other point you're gonna draw F3. So remember, you're gonna start with the force that is already fully defined, and you do have 2 points, start point and end point. Once you draw, and you have to put the direction in the same direction as already given here. So we finished F2. Now we would like to draw F1 and F3. It's up to you. You can draw F1 from this point, from the start point, or the end point. If you draw F1 from the start point, you have to draw F3 from the other point. 1 point for the 2 forces. Each force makes 1 point. So let us, for example, start drawing F1 from the start point, but you can do it from the end point. You're gonna end up with the same result. Okay, so starting from the start point, you're gonna draw a line that is parallel. What we know about F1, we just know the direction, and we know nothing about this force, right? Except the direction. So what we're gonna do, we're just gonna, from this point, draw a line that is parallel to F1. F1 it is horizontal, so you're just gonna draw a line that is completely parallel to this force in this way. This should give us the locus of F1, but where is the end of this line? We don't know. We start from this point, moving to the other point, or even from the other point that we don't know where it is, going to the start point of the F2. We don't know the direction, whatever it is, right or left. Even we don't know the length of this F1, how much it is, we don't know. So that's it for F1. So we finish F2, we finish F1. Now move to the F3. F3 has 3 unknowns. 2 unknowns. Magnitude and direction. We don't know nothing about F3. So what you're gonna do in this membrane, which should be drawn as well, because this should be drawn to scale, what you're gonna do, your objective is just to draw an extension of F1 and another extension of F2. So these 2 forces will be intersecting in a point. We should have something to generate the third line for the F3 to close the polygon. The polygon should be closed. So these 2 intersections, they're gonna intersect in a point. If you connect this point to the point over which F3 is acting at this point, let us give it a name like point A and B. So you're just gonna connect this point of intersection, let us give it like C. And you're just gonna connect this point C to point A. Why we're gonna connect this one? This gonna give us the line of action of the third force. As an essential requirement of a membrane that is subjected to 3 forces, that if we try to extend the line of actions of the 3 forces, all these lines of action should be intersecting at 1 point to achieve a static equilibrium for this membrane. This is one of the specifications of the 3-force membrane. Like what we did for the 2-force membrane, we said that if we extended the line between the 2 ends of the membrane, this is going to give us the line of action of the forces acting at the 2 ends. Here for the 3-force membrane, if we extended the line of action of the 3 forces, they should be meeting or intersecting together at 1 point. So simply if we extended F2 and extended F1, both they're gonna intersect at a point. This point also, if we connect it to point A, this is gonna give us the direction of F3. So we got the direction of the force F3. So what you're gonna do from the other end, so we said that we're gonna choose one end to draw the line for F1, and we did it. How about the line from the other end? Your objective is just to draw another line that is parallel to this line, to the new line that we already got from this membrane. So if we draw a line here that is parallel, we're gonna end up with another, this is gonna be this purple colored line. This is the line for F3, and this brown color, it is the one for the F1. So then your objective is just to close the shape, just close the polygon as already given here. So if this is F1 Remember, like this should be F1 direction, and this F2 direction, and this should be F3 vector, right? Now we have to, so if you measure this distance, this is gonna give us the magnitude of F3 by scaling it back. Like you just gonna measure this distance, how much it is, and you're gonna reverse this scale, you're gonna end up with F3 as magnitude. And this line is gonna be its direction, but you have to specify whatever it is going up or down. What is the direction of this force? Make sense? Also, the same thing works for F1. F1, we have its direction, but how much is its magnitude? Your objective is just to measure this distance, how much it is. You're gonna come up with the direction, with the magnitude of the F1 by reversing the scale. But now, how about the directions? These three forces should rotating in the same direction. You can specify the direction of F1, either right or left, or F3, either up or down, depending on what, based on this essential specification for this three force membrane. Like these three forces should rotating in the same direction. Like if this is the direction of F2, F3 it should be following in the same direction, F1 should be rotating in the same direction. So the exact direction of F1 is going to the right, the exact direction of F3 is going up. This is how we can do force analysis for a three-force membrane under static condition. Make sense? So this is the second case, and this is very important case, and we're gonna use this thing all the time. We basically, in many of the cases, we start with the force that is already fully defined. And from one end, we're gonna draw the one force, from the other end, we're gonna draw the second force. If there is one of the forces that is completely unknown, we have to specify its direction. How? Extend the two forces with given directions, they're gonna intersect in a point, then connect this point to the point of action of or the point at which the third force is already acting. You're gonna end up with its direction. Draw a parallel to close the polygon. This is gonna be the force polygon that we already discussing, this one. Make sense? So this is simply how we can do analysis for three force membrane, and this is one of the essential things that we are going to consider. Make sense so far? Now let us move to the two force uncoupled membrane. Like assume that we have a membrane and there are two forces acting at its ends, two forces acting at its end, such a way that one force at one end, one force at the other end, but there is, in addition to these two forces, there is one torque that already acting at a point belong to the membrane, like acting between the other two forces. A typical example of this two force uncoupled membrane is this one. Like assume that we do have this membrane in this way, like this is the membrane, and these are the two ends. So we do have one force at one end, there is another force at the other end, plus there is a torque. So assume that there is already a torque acting at any point, whatever it is, just to give rotation in this direction or even the opposite direction for this membrane, this torque. We can give this torque as T or M, it is couple or moment or torque, it doesn't matter, just something that is gonna give rotation to, or couple that gonna give rotation to this membrane. And there should be some forces acting at the two ends of this membrane. Okay, so if we knew the direction of one of these two forces, let us assume that the direction of one of these forces is already given. This is the direction of the first force as F1, and we don't know anything about force 2 in terms of magnitude and direction. So it is fully unknown, but this one, for example, F1 even, it is unknown. So we do have here F1, it is with unknown magnitude, but we know its direction. F2, it is fully unknowns. So remember that we already limited for just three unknowns, but the torque, it is fully defined as direction and magnitude. The torque is given as value. Let us assume that the torque is given by 40 Newton times meter. But the force is already having, this one is its magnitude is unknown, this is fully unknown, and this is the torque is already given to us as magnitude and direction. Its direction, it is either clockwise or counterclockwise direction. Make sense? So how we can find these unknowns? It is very simple. There is no force polygon that we're gonna draw for this case. Like the two force member, we didn't draw for the two force member any force polygons, right? But we just draw a force polygon for the three force member. For this one, there is no need to draw any force polygon, but we can do some calculations to come up with the F1 and F2. How? Your objective is just to draw something that you should understand about this membrane. Like these two forces, they should be equal, of the same magnitude, and they should be parallel but of two opposite directions. It is very similar to the two force member, yes, but because of the couple, there is a difference here. Like F1 and F2, both should be parallel and they should be equal, of the same magnitude but two opposite directions, but their line of actions will not be coincident. But in the two force member, the line of actions, the two forces were considered to the line that connect the two ends of the membrane. But the line of action of this one is going in one direction, as already given to us. This direction was given, and the other one, that definitely its direction, it should be parallel to the other force, and its direction, one is gonna go up, the other one is gonna go down. We can specify their directions up or down to give in such a way that we gonna specify the direction in such a way that the moment or the torque that is going to be produced from F1 and F2, it should be opposite to the torque that already acting on the membrane to achieve static equilibrium. So for example, this membrane rotates in this direction, so I should have, if I choose the direction of F1 in this direction and F2, I said that they should be parallel, of the same magnitude but two opposite directions. If we assume these directions, it means that this F1 and F2, they're gonna give the same direction of rotation at the torque. So this direction is not the correct one. To achieve static equilibrium, we should pick the direction of F1 in this direction, and F2 it should be the opposite direction, in such a way that both they're gonna produce a torque or a moment that gives rotation opposite to the rotation that would be produced because of the applied torque. Make sense? So this is for the directions. Simply, this is how we can specify the direction of the two forces. Now we still need their magnitude, how much it is. We can find the magnitude from this equation, that the torque equals F times H. What is H? H, it should be, if you draw a line that is perpendicular to either one of them, it should be definitely equal, perpendicular to the other one. If you draw a line that is perpendicular to F2, definitely it's gonna be perpendicular to the F1. Why? Because these two forces are parallel, right? So this distance that you're just gonna measure, this distance is gonna give us H. This H, remember that this H, it is not necessary to be equal to the length of the membrane. H here is not the length of the membrane. Okay, so I'm just gonna do a little bit changes here to the drawing to not be confused. And don't mix between the length of the membrane and the H. H, it is the distance of, or the length of the normal to the two membranes, to the two forces. Okay, so let us assume that the force, the direction, let us assume that the force F1 was given in this direction, vertical. Okay, so simply, automatically this force, if this is the direction of F1, this should be the direction of F2. Both these should be parallel, of the same magnitude but two opposite directions. The torque rotates in this direction, so F1 it should be going up and F2 should be going down to produce a torque that is opposite to the applied torque. Make sense? Then if you draw a line that is normal to F2 or F1, the length of this line, it should give us H. So as long as we already generating this thing with a scale, we're gonna draw this link with a scale. So automatically we can measure this H will be measured. Once we measure H and plug it here, you can come up with F. So then we can say that the F equal to the torque value, which is already given by 4 Newton over meter, over H that you're gonna measure here. to end up with the magnitude. This is going to give us the magnitude of the force F, and definitely you should understand that the magnitude of F1 equal to the magnitude of F2 equal to the magnitude of the force that we just calculated here. So this is how we can find the magnitude and specify the direction of these two forces for the case that you do have a membrane that is subjected to two forces and a torque. As you can see, there is no force polygon. We can directly come up with these directions and the magnitude, but with some simple drawings in addition to some simple calculations. Make sense? So these are the three cases that we're gonna experience many of them in the different mechanisms that we're gonna consider, right? So we consider the case that we do have a member that is subjected to two forces, and which is the two force member. Then we consider the three force member, and then we consider the two force and couple member, right? Now let us move to the general case. How about if we do have a membrane that is subjected to some forces at the ends plus so many forces in the middle plus torques? Everything is included in one membrane. So this is the most general case, right? So to consider this one, because it is a little bit lengthy, I had to explain to you these simple cases first. The two force membrane, then the two force with couple, then the three force membrane. So we're gonna use the thing that we already fixed it up there. We're gonna consider them for the general case of a membrane. So for the general case, we're gonna have, as I mentioned, for this one, we're gonna have, in addition to two forces at the ends, we're gonna have multiple forces in the middle. In addition, we may have a torque, or even more than one torque in the middle. So let us consider this case of the member. Like we do have, this is the member as already given to us, and this member is subjected to some forces, like two forces. One of the forces, F1, is already given in this direction, so it is fully defined in terms of magnitude and direction, and F2 is already given also in terms of magnitude and direction. In addition to these two forces, there is another torque that already acting in this direction, and the magnitude and direction of this torque is already given. So all of these forces that located inside, somehow this force is already acting at this point, and this force is acting at another point. And at these two ends, we should have two forces, but one of these forces is already given as direction, like the direction of the first force is already given, but we have nothing regarding the second force. So we're gonna assume that this is like F3 and this is F4. So for F4, we do have, or let us start with F1. F1, it is fully defined in terms of magnitude and direction. F2, it is fully defined in terms of magnitude and direction. F3, it is fully unknown. We have nothing to know about this force, and we have to solve for this force. And the F4, its magnitude is unknown, but its direction, it is already given. Like its line of action, it should be working in this vertical direction. Make sense? So this is as given. As you can see, we would like to handle or to do force analysis for this member. What we have to do is to combine all of these forces into one force. Even we're gonna combine to this force the torque. So it means that we would like to get rid of these three things that already located in the middle, and we're gonna combine them into an equivalent one force. To reset back again to the three force members, we can do analysis for the three force members. So we're gonna do two things, or three steps basically, that we're gonna have to consider them for this type of member. First, that we have to combine these two forces that already fully defined, F1 and F2, in one force. So this is step one. Then step two, we're gonna work on combining the resultant force, which is the summation of the F1 and F2. This resultant force, we're gonna combine it with the torque, with an equivalent force. So we're gonna end up with two equivalents. One force, which is the resultant of these two forces, then another equivalent that is the equivalent of the resultant force plus the torque. So we're gonna end up into just one force in the middle plus the other two forces at the ends. It means that we're gonna end up with a three force member. So we can do analysis for the three force member as we explained before. This is gonna be the third step. Make sense? So let us assume some numbers here for F1 or there is no need even, whatever the value for F1. So let us assume, even give some numbers. So let us assume that the magnitude of F1 is already given by 40 Newton, and the magnitude of F2 is already given by 50 Newton, for example, or 60 Newton, and the torque is already given in this direction, and its magnitude value, it is already given by, let's say, 100 Newton times meter. Okay, so, or let us just to have like a good scale here. So this is like, assume that this is like 10 Newton times meter. Okay, so assume these different values for the torque, the force, and so on. And the objective again is just to combine or do force analysis to come up with these three unknowns. Remember that we are limited for just three unknowns: the magnitude of F4, the magnitude and direction of this F3. So the first step, actually, step one here, is just to find the resultant force of the F1 vector plus the F2 vector. So this resultant force, we're gonna call it like FR. If we're already working in the force analysis, even if we decided to work analytical, this one is fully defined, this one is fully defined, this is unknown, right? So this is like the case one in the position analysis. We're gonna do it. If we decided to work analytically, we can do it the same way as we did it for the position analysis. Make sense? So we can find this resultant force. And remember, according to this loop closure equation, that this F1 and F2, they should be rotating in the same direction, but FR, it should be in the opposite direction according to this equation. This R, this FR, this is the resultant force that we are seeking for this membrane. So first of all, we should have the member already drawn. So let us redraw again this member, assume that it is already given here. So let us assume this membrane, I did a little bit change than the previous one, but it doesn't matter, it's gonna be the same way. I'm just give some physical numbers here. So this is like F2, it is fully defined, this is one force, and this is F3, this is fully defined force, in addition to the torque. And at the two ends, we have two forces. The first force, which is F1, and there is at this end, there is force F4. F4, it is fully unknown, we have no clue how much it is, but F1, it is already given, like it is already given, its direction is already given to us. Assume that the direction of F1 is this direction. So just let me make sure that it is drawn correctly in this way, and this is gonna give us the direction of F1. So this is the direction of F1. Make sense? And again, the F1, it is with unknown magnitude, but the direction is already given. F2, it is fully defined. F3, it is fully defined, but F4, it is unknown in terms of magnitude and direction. So these three unknowns, we would like to come up with these three unknowns. So the first step, as I mentioned, is just to find the resultant of F1 and F2, or in this case, this is gonna be the resultant of N2 and F3. We're gonna combine them into FR. So this is gonna be the resultant of these two forces. So how it works? First of all, we're gonna draw a force polygon just to find the result. For this step, we're just gonna draw a force polygon for the calculation of the resultant of these two forces. How? Your objective is just to draw the two forces that already fully defined, as we did before. We're gonna start from the O0. So this is gonna be the O0 point, the original point, OF point. This is the 0 point. Then your objective is just to draw a line that parallel to these two forces, or you're gonna draw the first force and the second force after you pick a suitable scale. So for example, let us assume any scale, whatever it is. I'm just gonna assume that the 400 Newton, I'm just gonna draw this one like 4 centimeter, and intuitively the 200 Newton is gonna be drawn as 2 centimeter, or you can scale it up a little bit, it's up to you. So I'm gonna start with F3. F3, so from this point, you can start even with F2, it's up to you. So let us start with F3 equals 2 centimeters, which is equivalent to 200 Newton. You're just gonna draw a line first. I'm just gonna draw a line that is parallel to this F3. in this direction. Then over this line, you're just gonna measure, starting from the zero, you're just gonna measure 2 centimeters and mark a point. Then you're gonna go over this line one more time to give you the F3, and this is the direction of F3 vector. Then from one end, you're supposed to draw the F2, or in other words, this is what we explained in the three force member analysis, right? We said that you're gonna draw one force from one end, and the second force will be drawn from the second end. No, you're gonna start with either one of them. We're gonna start with F1 and F2. Then you have to draw from the end of F3. I started with F3. From the end of F3, you have to draw F2. But if you started with F2, you can start with F2. That is fine. So you're gonna start from the OF, from the 0 point. You're gonna draw the F2. Then from the end of the F2, you're gonna draw F3. Both options, we're gonna end up with the same resultant force. So again, starting from the 0 point, you're gonna draw F3. Then from the end, we have to draw F2 from the end of F3. If we started with F2, you're gonna draw F3 from the end of F2. Make sense? So from the end of F3, I'm just gonna draw a line that is parallel to F2. I'm gonna draw a line that is parallel to F2. This line is gonna go down here. So this is gonna be the second line, which it should be parallel to the F2. From the end point, just draw a line that is parallel to the F2. Then starting from the end of F3, you're just gonna draw a line, measure the value of F2, which is 400, which is equivalent to 4 centimeters. So you can measure 4 centimeters either up or down. Which direction? Follow the same direction of F2. F2 is going up, so I have to go up in this direction. So I'm gonna measure over this line. Let me extend this line a little bit. Then I'm just gonna measure over this line 4 centimeters. So it's gonna give me this point. Then your objective is just to connect these 2 points together. This is gonna give us the F2. So remember, since we are calculating, here we are not doing analysis. We're just finding the resultant of 2 forces. This is different than the analysis that we did before. In the 3 force member analysis, we said that you're gonna draw one force from one end. The second force should be drawn from the other end of the first force that you draw, the fully defined force. But here we do have 2 forces that are already fully defined. So you're gonna draw one force. Then from the end of this force, you're gonna start drawing the second force in the same direction. They should follow the same direction. They should rotate following the same direction, like F3 going in this direction, then F2 as already given here. Then the line that closes, your objective is just to close the shape, just to connect this point to this point. This line that closes the shape, this is gonna give us the resultant force. And remember that the direction, according to this loop closure equation, that the direction of the resultant force, it should be to the opposite of F1 and F2 and F3. It means that F2 and F3 goes in this direction, the FR, it should be opposite. It should be opposite to them. So this is gonna give us the FR direction. Then your objective is just to measure it. Measure this value. You're gonna end up with a specific value if you're already working with a scale, and definitely this is what you're gonna do. You're just gonna end up with a value for FR. So this is the magnitude value for the resultant force, and this is its direction, that it should be closing the loop, closing the polygon or the force polygon, and it should be closing the loop going opposite to the F1 and F2 and F3 direction. Make sense? But there in the 3 force analysis, we draw one force from one end, another force from the other end, and all the 3 forces were rotating in the same direction. This is in case that we are doing analysis. But to find the resultant, the resultant, it should be on the other side of the loop closure equation. It means that it should be rotating opposite to the direction of rotation of F2 and F3. Make sense? Then what you're gonna do, so we got the FR and we got its value. Then you're gonna go back again to this drawing. Your objective is just to extend. What we're gonna do, we're gonna extend this force. Then we're gonna extend this force. So both they're gonna intersect in a point. From this point of intersection, what you're gonna do, you're just gonna draw FR, which is the resultant force that you just got here. You're just gonna draw a line that is completely parallel to the FR and going to the same direction of RR to locate this force over the member. And this is what we're gonna do. So your objective is just to, starting from this point, you're just gonna draw a line that is parallel to the FR that you got. So that's why this polygon should be very close to this drawing, and everything is drawn to scale. So you're gonna draw a line that is parallel to this FR going in this direction. This definitely gonna give us the FR that we just calculated. This is the FR vector, and now this FR is fully defined. So this FR can replace these two forces. Now we can cancel this force and cancel this force. So now we combine these two forces into just one equivalent force, which is this FR. This is the resultant force. So now we end up with a member of one force F1 at this end, another force at this end, and these two forces had been combined into one force, and there is one torque. Make sense? So this is how we can combine forces that already fully defined, located in the middle of a member. We can combine them into an equivalent resultant force as already given here. Make sense? Now what we're gonna do, the objective now is to combine the torque with the force into an equivalent force. Is to combine the torque and the force into an equivalent force. So how we can do this? First of all, you're just gonna calculate value which h. Because the torque, to combine this torque and force into one force, this equivalent force, it should be like you're gonna draw another force that is completely parallel to the FR but shifted from this point. This is the point of intersection of FR with the link or the member, right? So your objective is just to draw another force that is completely parallel to this original force but shifted with a vertical distance with a normal distance equals h. This h, if you gonna multiply the new force that we are going to locate, the new FR. So you're just gonna do like a shift of this force with respect to this point to produce a moment that is equivalent to this moment, or to produce a torque that is equivalent to this torque following in the same direction of this torque. And this is what we're gonna do. But what is the normal distance? The normal distance should equal to h. This h we can calculate it using this formula. So first of all, you're just gonna calculate h. This h is gonna be the torque value divided by the FR that we just got it. You should end up with a specific value for FR. From the calculation, we're gonna get FR equals 310 Newton. If we draw this thing in a scale, we're gonna end up with this value. So if you divided the 1000, which is 10 to the power 3, divided by 310, this is gonna give us 0.3322 millimeter. Or meter, I'm sorry, because the unit is Newton meter. So this should be the h value. Your objective is just to multiply it by 1000. You're gonna end up with 332.2 millimeter. So this is the h value in terms of millimeter. And remember that you have drawn this thing into scale with a specific scale. So you're gonna scale this value to match the scale of this drawing. You're gonna scale this value to match the scale of this drawing, and it's gonna be clear when we consider a complete example, right? So once you scale this value, your objective, you're gonna draw from this point of intersection of the resultant force of FR, you're gonna draw a line that is normal, that is perpendicular to this FR. This line, this brown line, it should be perpendicular to the FR. This angle, it should be 90 degrees. Then over this line, you're gonna measure h to the right and mark a point, and h to the left and mark another point. So we got 2 points. Then your objective is just to try to draw a force. So for example, if we decided to draw a force that is parallel to the FR and following in the same direction that from this mark on the left. So we're gonna end up with this FR. This is the new FR, this is FR dash. Which this FR dash, it should be with the same value, with the same magnitude, with the same direction, but shifted with h value that we just calculated. So this FR dash will produce a torque about this point. If I ask you how much is the torque of this force FR dash about this point, it's gonna be FR dash times h. This FR dash times h is gonna give us 1000 if you try to do the calculations. Make sense? But what is the direction of this torque? If I ask you to move this R to go to this point, or find the moment of this if r dash about this point, if r dash is going to go to in this direction, right? Is this direction the same direction at the given torque? Yes. So this is the correct position, and this is the correct direction of if r dash. Or anyway, the direction, it should be parallel following the same direction. But to draw this if r dash, I do have two options. I do have either to draw the if r dash to the on the left of the original if r, or I can draw if r dash to the right of the original. This is going to be another option of the if r dash, to the right of if r. If you draw it to the right and try to find the moment from this right force, the force on the right, this moment direction, it will be opposite to the given torque. So this one will be rejected. This is not the correct one. The correct one is the one on the left. So your objective, so it works in this way. Again, I'm just going to repeat it. Your objective is just simply, the objective now is just to combine this FR with this torque in one force. Make sense? But this one force, it should be parallel to the original FR force. We already removed these two forces. So we're gonna draw another force that is completely parallel to this force with the same magnitude but shifted. Shifted with a distance. This distance with a normal distance, this normal distance is h. How we can find this h? Divide the torque by the FR. These are the two things that we would like to combine. Define the force by the torque by the force. You're going to end up with h value. Then you're going to scale it depending on this scale that you already used for generating this drawing. Then you're going to draw a line that is normal to the FR from this point of intersection with the link. Or any point, but make sure that it is especially from the point of intersection to the link. Then you're going to draw a line that is normal to the FR. This line, you're going to measure over this line h, either to the right or to the left, depending on what? Depending on the direction of FR and the new FR, which and the moment that would be produced from this new FR. It should be in the same direction of this moment. So I do have two options, either to have FR to the left, on the left, or the right. The right is going to give me a moment that is opposite to this moment. So this one will be rejected. So I have to proceed with I have to mark a point on the left. So your objective from this point, you're just going to measure h over this normal line. Then mark a point. From this point, you're just going to draw a force that is parallel to the original force FR. This is going to be the new FR. This is going to be FR dash. And you should understand that this new FR dash, it should be with the same magnitude 310 at this one, and should be normal to this normal distance in this way. Then we can get rid of, remove this FR and remove this torque. So now we combine all of the forces that already located in the middle into one force. Even we combine the torque into just one force. So now we end up with a member with three forces. This is three force member that we explained before. That we do have one force in the middle, and we do have one force at this end, another force at this end. Now the objective is just to find these three unknowns. So now we have applied two steps. We combine first these two forces into one force, FR, then we combine the FR with the torque in one force. If there is no torque, so the second step is not needed. We already got FR and that's it, right? So your objective is just to combine as much as you can till you end up with only one force in the middle, in addition to the other forces at the ends. This is going to give us the three force member. Now, the objective is just to do analysis. Now we're going to do the analysis. All of the previous things, we were combining forces. We were finding resultants. We didn't do any analysis. Now we have to find these unknowns by doing analysis for these unknown forces or the three force member. Typically the same approach that we applied before. So we're gonna draw here, I'm just gonna use this side to draw a force polygon for these three forces, FR dash, the F1 and the F4. F1, it has only direction, but its magnitude is unknown. This is totally unknown. The one that is fully known is the FR dash. Its magnitude is 310, so you're gonna scale it. So the 310 Newton. I'm just gonna draw this one as we kind of defining by 200, so it's going to be like 3.1 centimeter, right? So this is going to be the scale. You can use even the same scale, or you can use a different scale. It's up to you. You can change because you're going to work over a new force polygon. So it is not necessary to follow the same scale that you use for any previous force polygon. You can use the same scale for all the force polygons, or you can change them. It's up to you. Or basically, this mainly depends on the values of the forces that we're already dealing with. So I can use the same scale, 3.1 centimeter for this FR, starting from the F0. So this is gonna be the O0. I'm sorry, the OF, which is the 0 point for the first polygon. Then I'm gonna draw this force. This force is going up. So I'm gonna draw a line that is parallel to the original force, parallel to this FR in this direction, and it should be going up. So I'm just gonna measure going up, starting from this point. I'm just gonna measure 3.1 and mark a point. Then I'm gonna connect these 2 points together. This is gonna give me the FR, the resultant force, which we just got it. This is the FR vector. Make sense? Then now we're gonna do analysis. So what does it mean? It means that from one end you're gonna draw one force, from the other end you're gonna draw the other force. Make sense? So starting, for example, from the start point, I'm gonna draw F1. So I'm gonna draw a line that is parallel to the F1, line that is parallel to the F1. So it's gonna be going down here. But how long, how much is the length of this line? We have no clue, because F1 it is not known. Even the direction going down or up, we have no clue. Then from the other point, I should draw a line that is parallel to the direction of F4. But F4, I don't know any direction for F4. But as we explained before, for the three force member, like the three forces, they should be considered together and meeting together at a point. So your objective is just to extend all of these three forces. I'm just gonna extend the F1. Then extend the FR. So both they're gonna intersect in a point. Then if you connect this point to the point of action, or at which the F4 is acting, which is this point, just connected, you're just gonna end up with the direction of the F4. This line gives me the direction of the F4. So now from this point, I'm just gonna draw a line parallel to this line, in this way. It's going to intersect with the previous line in a point. So if you set up a line between these 2 points and set up another line between these 2 points, this is gonna give us definitely the F1 vector, and this is gonna give us the F4 vector. And if you measure them, if you measure this one and measure this one, you're gonna end up with the magnitudes of these two forces. But how about their directions? We said that for the force analysis for three force member, the direction of all the forces should be rotating following in the same direction. Like if we start from here, this is gonna be FR, so this should be the direction of F4, and this should be the direction of F1. So what does it mean? It means that F4, it should be going up. This is the correct direction of F4, and the direction of F1, it should be going down in this way. And remember, if we measure this length and measure this length and we reverse these dimensions, we're gonna end up with the exact magnitude values of these forces. And by this, we already did analysis, a complete analysis, and we found all the unknowns for this general member. With lots of forces were located at the middle in addition to a torque. We combined them into a resultant force. Then we dealt with this member as a three-force member, and we did the analysis to come up with the unknowns. Make sense? So this is how we can handle or deal with a general case of member. And this, you could say that all of these cases that we explained here, these are the cases that we're gonna experience or we're gonna see or use through the analysis of the different mechanisms that we are going to consider for this part. This is simply how we can do static force analysis for a mechanism. The dynamic force analysis is typically the same, nothing new. It's gonna be the same approach, but instead of having some external forces acting on the member, especially if we're already dealing with three-force member. In the three-force member, we do have one force in the middle, this force like kind of external force, plus there are some other forces. These forces are the reactions at the supports, because this link, it should be linked with some other links to form a mechanism or to form a structure, since we're already working in static, right? So this external force, if this is a mechanism, is going to move. So there should be some inertia force. And we calculated on the top here that the inertia force is related to the mass of the member. So this member will be given a mass and it will be given an acceleration. So if you multiply the acceleration time the mass of this member, you're gonna end up with the inertia force of the member. So plus the external force, that would be acting on the member, there will be in the dynamic state, as long as this is a mechanism that is going to move with an acceleration, and if this member has a specific acceleration, you're just gonna multiply the mass of this member times the acceleration to end up with the inertia force, and you're gonna add this inertia force here to the external force. So we're gonna end up with like two forces. One force is the external force plus the inertia force. Then you have to combine these two forces acting in the middle. So we're gonna move to the general case. When we move to the general case, we have to combine these two forces into one force to end up with a resultant force to this membrane. Then we can find the reactions at the ends, right? Even if this link is going to rotate, if the link is going just to move, so there will be some inertia force, but if it's going to move and rotate, so there will be inertia force and inertia moment or inertia torque. This is what happens in the dynamics case, right? So it is very similar to the same thing, but in the dynamic case, in many of the cases, most of the links will be considered as the general case, because we're gonna have torque. Definitely we should have a torque due to the rotation of the link, due to the inertia of the rotation, the inertia moment due to the rotation of the link, plus some inertia forces will be located in the middle. So in many of the cases, in the dynamic case, when we do dynamic force analysis, we're gonna deal with the member as a general case. Make sense? And this is what we are going to discuss now. So for the dynamic force analysis is to determine the forces acting on an object by considering its dynamic equilibrium. So what does it mean, dynamic equilibrium? The dynamic equilibrium is achieved as long as the object is moving with an acceleration. It means that here the acceleration will be with a value. It won't gonna be zero at the static case. As we mentioned, that since we do have an acceleration, that any object with a specific mass, it will exhibit an inertia, either inertia force or inertia moment acting on this object, right? So even if you remember from the dynamic class that if we do have a moving object, whatever it is, this object, and this is the center of gravity, this is the mass center of gravity of this is this like the center point of this object, and if this object is already moving in the, let us work in the two-dimensional, like moves in the x direction and moves in the y direction in such a way that the acceleration of this point G in the x direction with a certain value, and it has an acceleration in the y direction of this point G. So this is the AGX and AGY. These are the acceleration of the center of gravity point, or the CG point, which is the center of this object. Plus that this object would be rotating, assume that it rotates in either directions with a certain rotation, so it will have an angular of acceleration as alpha. This is the angular of acceleration of this object. So because of the rotation, in addition to the movement, the linear acceleration, we should have, if I ask you to apply from the dynamic class, the dynamic equilibrium, that the sum of forces along x, it should equal to the mass times the AGX, right? And the sum of forces along y, it should equal to the mass times the acceleration along y. And the sum of moments about the center of gravity should equal to the IG, which is the mass moment of inertia about G point of this object, times alpha, which is the angular acceleration. And remember that this is the mass of the object, but this one is the mass moment of inertia. It is the mass moment of inertia of the object, which depends on the geometry of the object and its mass. The unit of this one, it is kilograms times meter square, and the unit of this one is just kilograms. And definitely this is gonna be in meter per second square, and this is gonna be radian per second square. Make sense? To give the force. Okay, so these are the equilibrium equations that we used to apply them in the dynamic class. But if I decided to deal with this dynamic problem like it is a static analysis problem, we can do so. Yes, we can do so by moving this, because what is the difference between this equation of the dynamic equilibrium and the static equilibrium, the difference is that the right hand side there should be zero, right? If we just plug this term equals zero, it means that there is no acceleration. We're just going to end up with the equations that already equivalent to the static, or the equation that we're going to consider for the static. But how about if I move these equations, these terms to the left side? I'm just going to move them with an opposite sign. So we're going to say that the sum of forces along x negative Fi, which is just inertial force along the x direction, equals 0. So I just call M AGX like Fi x. And the same thing, I'm just going to have here the sum of forces along y negative the Fiy equals 0. And the sum of mg, the moment, negative mi equals 0, which is just inertial moment. So with this mi, with this Fix, it equals the mass times the AGX, and this the Fiy, it equals the mass times the AGY, and the mi, the inertial moment, it is the Ig times alpha, which is the angular acceleration of this object. Make sense? So it means that is fine even if I said that this is like F. This is like F, the sum of forces along x, like another force F dash, for example, and I can combine these two into the sum of forces y along like F dash y, and this is like the sum of moments, the sum of m dash. It's gonna equal 0 and equal 0 and equal 0, which is the same thing like the static, right? We looks like we're already working as a static, right? This method, which is not that significant, that the conventional Newtonian method is commonly known as the D'Alembert principle. So it is commonly known as the D'Alembert principle. Like somehow we can handle this problem like it is kind of static, like equivalent to the static system. So that's why I started by reviewing the static force analysis, and we're gonna do the same thing as we explained here for the static force analysis. We're gonna do the same thing for the force analysis, but I'm just gonna calculate some extra forces, which are these inertial forces and moments, and then I'm gonna consider these forces or moment like external force. I'm gonna deal with them like any other regular external force. Like for example, as we explained for this case, this 200, this 400, this torque, these are external forces and moments. So for the dynamic case, plus these forces, we may have some other forces that comes from the inertia. So I'm gonna deal with these forces like the already also external forces, and I'm gonna add them here like external forces, and I'm gonna deal with them like any other external forces like the 400, like the 200, like the torque, and so on. So nothing will be new over what we already covered so far. Make sense? So how we can calculate this inertia force and inertia torque, and how we can put them over a length. So let us, for example, it is very simple thing. Assume that this is the length that is already given to us. Your objective is just to locate where it's G, its center point, where it is located. Then at this point, you should have information about the acceleration EG. You should have information about the acceleration of the mass center G. So assume that the acceleration EG, I'm just gonna give it uppercase G, this here to refer to the acceleration. So the AG, this is the acceleration. And remember that the acceleration, it is a vector, so it should be with magnitude and direction. So assume that we already given this acceleration, it is already given to us, AG in this direction, and even its value is already given. If it is not given, we have to do position, velocity, and acceleration analysis as we for this mechanism, as we did before in the start of this course, using either the analytical method or the graphical method to come up with the acceleration. But if the acceleration is already given, so there is no need, you can skip this part, and we're gonna discuss this point with more detail. So if this is the direction of the acceleration and its magnitude is given, you're just gonna calculate the inertia force. You're just gonna calculate the inertia force, which is Fi, inertia vector. This inertia force is should equal to the mass m of the membrane or the member times the ag, which is the acceleration vector that you already have. So your objective is just to calculate the magnitude. So you're gonna substitute with the magnitude of the force. So you're gonna end up with a value of this force. So this is the magnitude of the inertia force. And also its direction. How about its direction? This is the magnitude. Its direction, you're just gonna put it. So this is the physical inertia force. But according to the D'Alembert method, I'm just gonna consider, even if you remember from the dynamic class, the direction of the inertia force, it should be in the same direction of motion, in the same direction of the acceleration. If the acceleration is going up, the inertia force, it should be going up. So if I'm gonna deal with this force, like it is inertia force, it should be, we have to add it in this way, like Fi inertia force. It should be in the same direction of the acceleration. But I'm just gonna deal with this force like it is external force. So external force, to deal with it like external force, you have to put it in a direction that is opposite to the acceleration direction. It should be parallel to the acceleration direction, but opposite to it. So the acceleration going up, the direction of the inertial force is gonna be in this direction. This is gonna be the Fi vector. This is gonna give us the direction of the inertial force, and this is its value. This is how we can add the inertia in the dynamic case. And we're gonna deal with this force that already acting at this point G like it is external force. So if we do have another force at this end and there is one force at this end, so this is 3 force member. Make sense? But plus this force, how about if this link is already rotating? If there is a rotation to this link, somehow that this link rotates in this direction, alpha. So because of the rotation, there should be definitely a torque acting on the link, and the torque, it should be rotating opposite, because I'm gonna deal with the torque like it is external torque. But if it is inertial torque, it should be in the same direction of alpha. But as we agreed, we're gonna deal with this torque like it is external torque. So to deal with it like external torque, which is Ti, T inertia, that comes from the inertia force or the inertia moment of this member, this T inertia, it will be assumed like external torque, so it should be assumed in a direction opposite to the direction of the given alpha, which is the angular acceleration. Make sense? And then we can calculate this inertia torque. This inertia torque, it will equal to the I, which is the inertia moment about G of this member times alpha. We can use for this I lowercase or uppercase, it's up to you. Like this one, I can type this one like Ti, lowercase, it's up to you. Make sense? So this is for the, this is gonna give us the value, and again, the direction of this torque is gonna be opposite to the direction of alpha. And then we're gonna deal with this force and torque like external forces, eluding, acting on the member, and we're gonna consider this member as a general member as we explained even in the static analysis. So nothing different between the static or the dynamic analysis of the mechanism or this structure if we're already working in the static case, except these inertia forces, that even we're going to deal with them based on the D'Alembert method or approach as external forces. Make sense? So this is for this introduction, and the important is just was to show you how we can do force analysis for these different types of the membrane and the difference between the static force analysis and the dynamic force analysis. We're gonna focus through this part over the dynamic, because this is the objective of this course. We're already working over mechanisms, so the mechanism should be moving, and many of the cases it's gonna be moving with different accelerations. So with an acceleration value, it means that there should be some dynamic effect or inertia effect due to these inertial forces or moments of the generated due to the rotation of the members. So we're gonna consider the dynamic force analysis based on the thing that we already discussed so far. The next video, I'm just gonna show you an example how we can do force analysis for a mechanism with more detail, going over the general steps for the dynamic force analysis of a mechanism graphically, using the graphical method. Thank you, and that's it for this video, and see you in the next one.